of your experimental lab sheet on the temperature control system. In this lab, we have to reach two objectives. Firstly, we would like to observe and explain the operation of open loop and closed loop temperature control systems. Then we analyze the performance characteristics of open loop and closed loop temperature control system. Labvolt process control channel will be the main equipment to be used in this experiment. This slide shows the front panel of Labvolt process control channel model 3521. In the first part of the video, I will emphasize on the power supply configuration for the trainer. And in the trainer, we have heater. You can see here we have heater. As such, we have heating element therein. From the block diagram, we notice that the power source, this is the power source to the heater. This power source is controlled by a solid state relay. We have a solid state relay here, a module here, and the purpose of this solid state relay is to control the power source to the heater. And this power source is the internal, which is built-in inside the trainer. We also have a fan. We have fan here. So the purpose of the fan is to cool up the radiator. We have a radiator inside. And at the left hand side, we have a column of multifarious supply generators. We have a noise generator, triangle wave generator. This is source 1 and this is source 2 supply. And in this top right corner, we have a moving coil, behave as a DC voltmeter to provide a measurement facility. And here we have a PID controller module. We can set our desired controller, whether proportional integral PI or PD, as well as PID controller. This slide presents the open loop configuration. If you have the lab sheet, you can observe the connection, where this connection is open loop configuration, and our plant is the heater. So we have our plant is a radiator. We have a radiator here, and this radiator is our plant, and we have power processing unit. In this trainer, our power processing unit is a solid state relay module here, and we have the supply. So this is the supply or input to our plant, and this is the open loop configuration of this temperature control system. The next slide shows the closed loop configuration of the temperature control system. The difference between the previous is the appearance of the controller box here. You can see from the configuration we have a controller where we use the proportional controller, and we have a feedback element, which is the temperature transmitter. In the radiator, we have a sensor. This is a thermocouple, and the thermocouple sends the temperature and send to the controller through this error detector, and this error detector will calculate the error between the demand and the output, and this will be the proportional control system for the radiator. Okay, if you can draw the block diagram, the control block diagram, I have a plant here. So our plant is a radiator. So this is our plant, and we have a solid state relay here, and we have another block, additional block we call P controller. So this is our controller, and we have a decision maker, which is error detector, and this represented by the summing block, and we have the source. So this is a DC source or demand, or I can write here DC source, and we have a control signal to the solid state relay. This is our solid state relay or power processing unit as previous. And you can see from the radiator we have a thermocouple, and this thermocouple sends the temperature through this feedback element. We have a sensor and feedback element here. I put here is feedback element block and send back the signal to the controller. So now you can distinguish between the open loop and closed loop temperature control system in this lab. Okay, we then go back to the slide 4. In the slide 4, I want to focus on the power supply to the radiator. If you notice from this figure, we have the solid state relay, we have a source, and we have a control input. Why we need this relay? Why we don't supply the heater directly from the source? Okay, why we need this relay and this triangle wave? If I draw the diagram, we have here DC volt supply, and I can draw here the supply. So the supply is 5 volt according to lab sheet. We have a 5 volt supply, and this is triangle wave generator where the signal is in this pattern, and what will be the output to the level comparator? So the output to the level comparator will be the square wave. So the purpose of this comparator is to produce the square wave signal to be sent to the solid state relay. So you have this DC level voltage, and we put here 5 volt, and we have a triangle wave here. And this will be the output of the comparator. Yes. Okay. We put here, this is the on level and this is off level, and this is the on time and this will be the off time, and this signal is sent to the relay. So this state relay, it is here to the relay. Okay, and from here we can conclude that when the relay on, which this means on time, and 5 volt to, sorry, it's not 5 volt, it's a source. This from here, this is internal source, and we represent as V2 to the heater, and then the heater on. When relay off, mean during the off time, and 0 volt to the heater. This is what we call pulse width modulation. Okay, why we need this PWM signal to control the heater? As I said just now, why we don't connect the heater directly to the power source? PWM is a digital unipolar square wave where the duration of on time and off time can be adjusted, or we can simply call can be modulated by adjusting the level of this DC source. This means you can increase this DC source, or you can reduce this DC source to adjust the on time and the off time of the relay, and hence adjust the on time the duration of supply from the source to the heater to heat the radiator. This way the power delivered to the heater can be controlled, where we normally don't allow the continuous source to be supplied to the heater to avoid it from overheat and become less efficient. That's why we need this PWM for the heater. That's all for the first part of the video. Thank you.